Hello, welcome to this edition of Silicon Grapevine, brought to you by Siemens Digital Industries Software. My name is Nitin Dahad with EE Times, and today my guest on the show is Sudarshan Deo, who's a software R&D manager for 3D ICs at Siemens Digital Industries Software. Sudarshan, hello, how are you?
I'm good, Nathan. How are you?
And fine, thank you. In this episode, we're going to talk about reimagining 3D IC design with AI, and we'll explore how AI is fundamentally reshaping both chip architectures and the tools used to design them. But before that, Sudarshan, as with all guests on this show, I try to go a little bit into the journey, the profile of the guest I'm talking to. So tell me, Sudarshan, how did you get into computer science, which is kind of how you started in this industry?
Well, I always had like an engineering, background running in my family. That was, one of the motivations. The upbringing was such that I always, saw engineers, right in front of my eyes. So that was one of the things. And then second thing was, right from childhood, it was, I always liked, Sudoku, logic building or, solving puzzles. So, I think that's where, my parents realized that I think engineering is going to be, like a suited career for this guy. So yeah, I landed here, I landed in computer science, I liked it in the first place. And then, it was always kind of a hit. But I think the motivation came in, later in the career when I started, exploring more towards, machine learning, or, when I entered into my graduate programs, that's where I realized I think I've chosen the right path, because, that's kind of, suiting my needs and, suiting, what the industry requires from me as well. So it's kind of working. Yeah.
I mean, you studied in Pune, Maharashtra, so that's where you started in India.
Right.
But tell us, how did you get your first sort of break into the industry?
Well, I worked for a couple of years back in India, in Pune, before I, pursued my master's here in Sacramento State in California. But, I was always ambitious to, learn, or get like a graduate degree and explore the world, right? So, it was never specific to a specific country or a specific region. But, coming from a computer science background, I always wanted to, be in the, quote unquote tech hub, so that was
Exactly.
one of the reasons, California was like a dream at that point in time. Well, it's still a dream, but it's been like more than 10 years I've been here in California, and now that feels pretty good. Yeah.
And how did you get your first break into the industry? Is that through?
So
I think you worked in
I
Intel, Synopsys, Cadence, and now
right.
Siemens.
So exactly. So while I was pursuing my master's in computer science, I had a specialization in convolutional neural networks, so CNNs, back in the time. It was in 2015, and I worked for a gaming startup at that point in time. Before I entered into the EDA industry. And one of the managers at Intel realized that back then they were working on those Intel Nirvana chips in 2017.
Yeah.
So Intel hired me as a component design engineer, or like a design automation engineer, where I started working on Intel Nirvana chips. And I think that was my first breakthrough into the EDA industry, coming from a pure software ML based gaming world into like a different EDA world. That time it was like pretty overwhelming for me. EDA as like a new industry for like a computer science grad. It was pretty new, but I think that's where I gained like foundational knowledge of RTL to GDS, or how EDA industry works in general. And then I worked as a design engineer for Intel, with Intel Foundry, with the Intel design team. And later in the stage, in my career stage, I had moved to Synopsys, where I worked on their 3D IC technology, right? So specifically, it was like integrating their advanced multiphysics solutions into their 3D IC flagship tools, right? So I think that's where I gained hands-on expertise on how quote unquote AI is kind of optimizing all of these physical phenomena within EDA industry. And later in my stage in my career, I moved to Cadence, where I focused on the intricate routing challenges that we see usually in 3D IC, right? So I was one of their lead R&Ds who was working on developing and integrating like 2.5D 3D IC advanced packaging routing capabilities in Cadence's flagship 3D IC products. Yeah.
And
and
then
and now
now,
I'm with Siemens. So I think the world is round. So now I'm with Siemens. I'm working with the central engineering team. It's
mm,
it's it's a central horizontal team within Siemens, and I'm managing a software R&D team. It's spread across multiple geos right now. So we have a center of excellence, design team in Cairo, Egypt. We have a team in Yerevan, Armenia as well, and then there is a team in US. So I'm kind of managing all the three teams.
I remember when I spoke to Wally Rhines quite some time ago. He actually established that center in Cairo in Egypt quite a few years ago. And he said it was one of the biggest centers for mentor graphics that time outside of the US. So we can see where that has evolved.
Right, and it's still evolving. I think we see one of the brightest candidates in Egypt right now, and I have a team, with one of the brightest mindsets. It's pretty young. It's a pretty energetic team.
Yeah.
I think they're diving deep into 3D IC. So yeah, it's pretty good so far.
And I mean, now we're in this age of AI and high performance compute. You know, everybody talks about 3D ICs being able to unlock that performance. Um,
Mhm.
just tell us, because like there's a difference between like for a while we've been talking about 2.5D and then 3D. Like, how do we define 3D IC, in or what's the key thing that we should understand about 3D ICs?
Right. I think I'll just give you a very simple analogy, right? So
Yeah,
at its core, right? So 3D IC, or 3D integrated circuits. It's basically
yeah,
referring to you stack multiple active dies, right, on top of each other, and then you basically connect them with a very short dense interconnect network, right, which we call through silicon vias, or TSVs.
yeah,
But basically you can think of it like a multi-storage building, right? So instead of creating like a horizontal campus that you create like a multi-storage building where
yeah.
you have different floors, and then it's kind of spread all over, like one on top of the other. So that's I think like a realistic analogy I would give for 3D IC. Well, why we are doing 3D IC? I would say it's basically it has like I would categorize those into like three factors, right? One is performance for the chips. Second is
Yeah.
the power efficiency that we have, and third is I think it's the form factor that we have, right? So basically when you think about performance, it's basically by stacking different dies, you are basically shortening the distance, like time to travel between different dies, whether it's like a CPU die or like a memory die or like any other die, right? So the shorter the distance, the faster the communication, and the higher the bandwidth. So that's the goal, right? So it's like imagining like a super fast lift in your building, which
Yeah.
which is basically able to connect between two floors, right? Second is efficiency in power, right?
Yeah.
So you have different chips that are operating at different power efficiency. So how can you move the data between the chips? And I think third is the form factor, right? So you have like a compact space in which you need to fit all of your chips, right? So I think nowadays, right from smartphones to high computing, it's like getting smaller and smaller. So how you do stack it up? So I think that is the biggest motivation that yeah.
And I think we've seen these images from all the EDA companies, including us ourselves, in terms of how that
Right.
sort of stacking
Stack builds up. Yeah.
yeah, the stack builds up, and not just yourselves. I think I've seen it at IMEC and various other places. But I think
Of
one of the things
course.
you missed out was cost as well, because
Of
what
course.
3D IC and heterogeneous ICs basically allow you to do is mix technologies depending on the performance required.
Yeah, cost, of course. I mean, that comes into the picture. It really depends on how you think about the cost, but I think that plays like a very vital role in terms of designing the chips, and in terms of manufacturing the chip as well. Yes,
That's right.
absolutely.
Now, we can talk about how AI plays into that, but before we do that, I guess what are the challenges of designing 3D ICs? And then we'll talk about how AI is being used both on sort of the architectures, but also on the design.
Of course, of course. I think that's a good question. So you're right. So whenever we see all of these fancy benefits that are coming out of 3D IC, I think it comes with its own complex challenges, right? So there are challenges in terms of how you build 3D IC as compared to traditional the 2D flows that you have been seeing so far, right? So as far as I have seen with different EDA vendors, with different semiconductor companies, I think the first challenge I think everyone knows is basically thermal, managing how thermal plays a role, right?
I hear
So
that all the
I think
time.
thermal,
Thermals.
yeah,
Yes.
I think
Yeah.
thermal plays a very critical role in in 3D IC right now, especially when you're stacking the chips like vertically. It produces a lot of heat, right? So imagine
Mm.
again the analogy, right? So you have like multi-storage building where you have different floors producing different heat, and then there is just one roof from where the heat escapes. So that's going to be a big challenge, right? So
Yeah. Yeah.
managing this heat to prevent like thermal hotspots, to ensure the reliability of your 3D IC, that's like paramount right now. So I think that's
Mm.
one of the key challenges that you have. I think power integrity, PDN, and then signal integrity, that's the other key challenge as well, because I think every active die has its own varying power that you see, right? So
Mm. Mm.
like without significant IR drop or like voltage drop, or maintaining all of those noise or power integrity issues, I think that's like a very huge challenge right now. I think the third I believe is once you build the chips, how long the 3D IC stack is going to survive, right? So it's
Okay.
basically the durability or the
Yeah.
reliability or the
Yeah.
lifetime of your chip, right? So different stacks are made up of different materials, right? So you have an
Mm.
interposer made up of silicon, organic, glass, and then you have a different packaging material, right? And then every material has its own expansion contraction ratio, right? So everything expands contracts at a different rate. So maintaining that mechanical stress or a warpage or delamination that you have, I think that's one of the biggest issues for long-term reliability. The other challenge I see is now since you have stacked the chips,
Yeah.
how do you make sure that they are functioning the right way, right? So testability, right? Design for test or verification. I think the traditional methods that you have for design for test are kind of not sufficient, right? So you'll
Mm.
have to have advanced methods to make
Mm.
sure that when you couple thermal versus mechanical or thermal versus electrical, it's kind of functioning pretty well, right?
Right.
And I think the last thing is once you have all of this, it kind of produces enormous amount of data. So
Yeah.
that data always is there, right? So managing that vast data, right, that comes from different workflows, different platforms, and then making it seamless across the design life cycle, that's a big challenge right now. So I think these are like the few challenges that every EDA company including Siemens is kind of facing, and then trying to address right now.
Well, I mean, when you've explained all of that, it sounds really, really complex, and especially with all the data. And I think that's where AI tools come in, I
Right.
guess. And so,
Absolutely.
tell us a little bit about how, obviously, everybody's talking about AI tools for
Hmm.
3D IC design, but tell us
Right.
specifically how it helps. And I
Of
mean,
course.
I've heard of
I
things
mean,
like the design space exploration and stuff like that, but there's a lot more
there you
to
go.
it.
There's a lot more to it, of course. And I mean, so again, AI is not it's not just a buzzword, right? It's like it's like a co-pilot, I would say, right now
Okay.
for
Yeah.
3D IC, right? So it's basically helping us tackle all of the challenges that I just mentioned in more of a profound way, right? So you mentioned about design space exploration. I think that's one of the ideal AI applications that we see in 3D IC, right?
Hmm.
So right now what we see is there are like a number of possible combinations that can come up for like a 3D IC design, right? So AI in particular, I mean, I would say like a subset of AI where I say like reinforcement learning or machine learning or like intelligent optimization algorithms that you have.
Hmm.
Basically they can help you explore like vast design space. They can help you identify like what are the optimal configurations that you can see for, let's say, power, performance, or area. A regular design engineer or like an actual human would take n number of years to actually figure out, right?
Hmm. Hmm.
So I think that's one of the crucial
So it's cutting the
things that we need.
time, and then
Exactly.
like the complexity.
Right.
Sorry, the bringing
And
all of that data together. Yeah.
of course, yeah, and especially that helps if you are early in your design phase, right? Especially when you don't have all of the layout information or all of the PDK information available from a design team or a foundry. I think at that point in time, if a designer wants to build a specific model, early in the architectural planning phase, I think design space exploration plays a very vital role, right? So that's
Mm.
one of the key things, right? I think the second thing is when you have like early predictive analysis or like early issue detection, right? So I think that plays a very important role, right? Where let's say for example, instead of waiting for like late stage simulations for, let's say, thermal, you're trying to identify where the hotspots can be at the early stage of your design. It's basically like a shift left approach that you see. And I think at the start of our meeting, we mentioned about cost as one of the parameters, right?
Yeah.
So I think
Yeah.
this is one of the key areas where you can, not even save time, but you can also save the cost in terms of, manpower, in terms of resources, in terms of your, chip building, life cycle as well. So I think that's the other key thing right now. The other things I can, think of is, you have, agentic AI, right? So now
Yeah.
let's, dive from, design space exploration to, where you can actually build like an LLM chatbot where
Yeah.
you can actually, send an input or like query using natural language processing, and then say that, I want to build like an actual 3D model which can help me, optimize the temperature, or, get me a desired temperature in certain, degrees Celsius, or can, help me, optimize by electrical parameters results in, XYZ manner. So, from there you can, basically have like an agentic AI, orchestration layer, which can, have like, multiple steps, right? So it can, help you like build the model, run the model, analyze the model, and then, feedback, using like a backpropagation method. And then, kind of, help learn the model itself, and then, kind of save time for you. So I think those are the key things, where AI can play a very, massive role, I would say, right now.
And then the natural question after this really is around, well, we hear from all of the companies in the industry, in the EDA industry,
Right.
saying we have these AI tools, we have the agents, we have the orchestration. Obviously, I'm speaking to you at Siemens Digital Industry Software. Tell us a little bit about the differentiation that Siemens provides in in enabling this.
Of course, of course. So at Siemens, basically we are taking, a very like, deliberate and like, industrial grade approach for, injecting AI within 3D IC, right? So our
Mm.
focus is basically, creating solutions that are, accurate, more verifiable, robust, and, generalizable, right, for our customers, because, we want to make it, as generic as possible, so that, it's pretty easy for, any given, foundry or any given design team to actually integrate into their, workflows, and, does not disrupt their, original, cycles or original flows that they have, right? So I think we are taking a comprehensive approach where we are splitting our AI model into like two phases, right? One is, of course, the design space exploration and the optimization model. So we have HEADS, which is our, hierarchical, evolutionary engineering, system disciplinary optimization model, which is the HEADS platform that we have. And
Mm.
of course, that's like a, design space exploration engine. It's a very powerful optimization engine, I would say,
Mm.
which is, helping engineers to make like, critical architectural decisions right now, trying to help them identify, problems early on in their designs, help them optimize the PPA, help them optimize the reliability, the thermal dynamics of their designs, and then basically help them find, best possible scenarios within, billion number of possible scenarios or permutations that they have, right?
Probably billions and
So
trillions, I guess.
billion and trillions, exactly. So it has its own like, surrogate model that, helps you, find the global minima within your design
Mm.
cycles,
Mm.
right? So that
Mm.
that's one of our phase ones, or one of the phases that we have. And second is, of course, we have the LLM or the agentic AI injection into our 3D IC workflow. So we have, Fuse EDA AI, which is our flagship EDA AI product for, generative and agentic AI integrations. And we have been using this across all of our EDA flows, within Siemens, not just, vertically, but horizontally as well, right? So I think that's one of our key things, right? So
That's internally
because,
then as well as externally.
right. So
Yeah.
I think vertical integration into the tools is always required, right? Where you have, a physical design tool or like a verification tool that has, AI injected into their own, solvers or models.
Yeah.
But I think we are taking a far beyond approach than, vertical, integration, where we are doing, horizontal AI as well, right? Like, for example, imagine you have an AI agent that is, monitoring your, power analysis results, right? And then,
Mm.
it has its intelligence to decide that, based on the power analysis, how can I trigger my thermal simulation? And based on
Okay.
the power and thermal simulations, how do I go back and then make changes in my design, right? Right?
Okay.
Make a change in either in my floor plan, or either in the placement, or, anywhere else. So I think
Yeah.
that's more of a horizontal approach, where, AI is kind of helping communicate between different EDA tools right now horizontally, as well as you have the vertical injection in the tools as well. So I think that's the approach that Siemens is taking right now for 3D AI.
Interesting. I like anybody who knows me. I like real world examples. Tell
Of
me
course.
some examples, either customer case studies or something that you can talk about that sort of shows both the addressing the complexity, but also solving, the time to market, I guess, which is one of the key things that people will be using the AI tools for to
Of course,
design
I
these.
think we have been, yeah, of course. I think that's a good question. So we have been engaged with, different, foundry customers, different design customers, right from, hyperscalers to, advanced packaging, foundries where, they have been using our, flagship AI products within 3D IC right now. So, most of our tools are actually certified for, almost all of the foundry businesses that we have been working with. And I think the feedback that we have got from the customers is it's not only saving their time or saving their cost, but it's also easy to integrate. It's kind of pretty generic where and in EDA we have seen that with several other customers. I think it's an open discussion that every foundry or every customer has different EDA tools, right? So they are not using like one EDA ecosystem. So I think the feedback that we have got from them is the workflows or the design flows that you have that helps us not just create a particular ecosystem, but different ecosystems as well, where they can plug and play with different EDA tools right now. So I think the integration is kind of seamless, and I think we have been using MCPs in our agentic AI frameworks, and then we have been using skills, which is kind of a hierarchical model where you define all of your steps, how you want to run it, and then you kind of inject that into your AI engines. So the overall feedback has been pretty good so far. I think we have been engaged with the top GPU companies, the top hyperscalers right now, within the US and then in APAC as well. So I think it's the feedback has been phenomenal so far.
Okay, I mean, nothing ever goes right first time. Tell us what are the
Of
things
course.
that can go wrong. Uh, I guess I'm not talking like with AI tools and AI agents. This I always hear about needing that human in the loop and oversight, but it's that, but also just what can go wrong with 3D IC design generally. And we talked about some of the challenges like the thermals and and all of that. So can the tools like underestimate, which then makes it difficult when it comes to implementation? Or just give us a few thoughts.
Of course, I think that's a fair question. I've been asked this question like in multiple forums. Always that
Yeah.
question comes up that where can AI go wrong? I think it's crucial and it's very critical to have like a very balanced perspective, right? So
Yeah.
I think while AI is like super powerful, like it's providing all of the knobs and hooks right now, but it's again we have to understand it's not like a magic box, right? So
Yeah.
it can
Yeah.
certainly have its own pitfalls, right? So I think if the data within AI is not carefully managed right now, so it can go either ways. It can give you like incorrect predictions or incorrect results, right? So I think it's more of kind like a garbage in garbage out model, right? So
Mm.
AI can be as good as the data on which they are getting trained on, right? So if the trained data is like biased, right, it's not complete, or it has incorrect labelings, right, or it contains errors, right? So then AI of course is going to be trained on all of those biases and then flawed models, right, and it's going to produce misleading results. So with 3ds it becomes far more important because you have different components getting connected to each other, right? So I think that's one of our workflow key things that we are working on, where we are trying to make sure that we pass on good data, we pass on filtered data, because not every tool understands how the other tool behaves. And I think 3D IC is more of like a flow management where you have different tools communicating with each other. So I think that
Mm.
that becomes paramount right now. And I think the second thing is like again I mentioned, right, it's more of a black box problem, right, that
Yeah. Yeah.
not every tool is kind of understanding what the other tool is doing, right? So basically I think what we are doing is we are helping AI make particular recommendations for the user, saying that there should be like a human in the loop, right, where we need verifiability not just from the system but from the designer or from the package engineer as well, that whether it's correct or not. Because I think we need that, because there might be like misleading outcomes that can come up, right? So it's always good to have that before there is a back propagation that goes back and then feeds into the model, right? So, and again I think the last thing I would say is the human touch is always required, right? So ultimately it's a tool, right? AI is a tool, right? So it excels at pattern recognitions, optimization or automation, right? So it has all of those capabilities, but I think at least now what it lacks is a sense of like like a common sense that a human has, a sense of ability to understand or a broader context or like,
Mm, mm.
unseen, circumstances or unseen applications that, a 3D IC has. So, a human intelligence, human judgment, critical thinking, I think that's always uh, a mandatory or like a key input that, AI will need, right? And I think this is going to, just help improve the PPA or, help improve the analysis that AI is gonna bring the picture.
I mean, one of the things I guess is everybody's now talking, and you did as well, about the orchestration of AI agents, and that's done by
Yes.
a super agent, for example. Like one of the companies talks about it. But where the agents are talking to each other,
Mhm.
what safeguards or whatever can you put in to make sure? Or I mean, what does Siemens do where you make sure that you do have that human oversight in the right places?
Of course. I think Siemens has a good amount of secure guardrails that it's putting, because we don't want uh, a foundry to have access to the data from B foundry, right? So that's
Yeah,
that's
yeah,
a very typical example that you see, right? So
yeah,
that's a violation of security, right? So that's a very
exactly.
typical
Yeah.
example. But just by looking at that, we also want to create like MCP servers and then skill models on which the customers can build their own skills as well. So we don't want to
Yeah.
restrict the
Okay.
customers to inject their own proprietary data or encrypted data that they cannot share with EDA
Mm.
partners, right? So we are
Yeah.
building models in such a way that it's secured. Of course, it won't be able to access foundry to foundry data or like customer to customer data, but
Mm.
we have skills files or skills modeled or MCP servers developed in such a way that we provide a baseline so that the designers can focus on the design specific activities and they don't have to worry about the EDA frameworks. But of course, they'll have their own data lake, where they want to port in their data lake, where they have release documents or quote unquote encryption documents that they can plug in, and then that will help train the data more seamlessly right now. So I think we are following all of those guardrails right now.
Now, given your experience, and I think maybe what I would like to sort of close on is, given your experience in sort of 3D IC design and over the last decade or so, what are the lessons you've learned, and what are the things you think people might want to sort of know from you about sort of things you've learned and they can experience?
Definitely. I think I'll give a personal touch, right? So I
Yeah,
think we discussed about this, that I came from a gaming, a startup world, and
yeah,
into EDA. But the key thing that stands out, and then I hold on to it, is continuous learning right now. So I
yeah,
think you should always embrace continuous learning, especially in 3D IC and AI, where the pace of the innovation is kind of fast forwarding right now. So what today might be like outdated tomorrow, right? That's what I've seen
mm,
in my past experiences as well. So I think you need to have like a continuous learning mindset. I think you should be very curious in terms of what's happening within 3D IC, because it's a pretty new world. There are a lot of challenges that everyone is trying to address. It's pretty much quote unquote in the R&D stage right now, although we see a lot of solutions, but still people are trying to find where the bottlenecks exist, find
yeah,
trying to find the right solutions towards it. So I think that's one of the things. I think second is, if you are working in 3D IC especially, you need to think from a system level, right? You cannot think on a vertical aspect, right? So don't get soiled by thinking just on the vertical aspect. So even if you specialize in one area, let's say physical design, or let's say timing, or thermal, you need to understand that how that impacts the entire system, right? Let's say
mm,
right from silicon to that, let's say the final product, right? So I think Siemens stands out here. I just want to touch base because Siemens is not just, I think you mentioned DISW, right, which is digital industry software. So Siemens is not just EDA, quote unquote, right? It
mm,
actually has its own PLM knob as well. It has its own STS, which is a simulation knob as well. So I think we are
mm,
thinking from a pure system perspective, right? From I would say, let's say silicon to rack, right, where you are building 3D IC within the package, but you are building 3D IC outside of the package as well, right? Where you have now your actual PCB getting connected to the board, connecting to the rack, and then actually connecting to the server as well. So I think you should think about that from a system level perspective as well. The other
interesting.
thing I touched upon is data. I think for me, data is like gold, right? It's right now
Mm,
it's pretty much gold. So
mm,
for AI to be pretty much effective, high quality, well standards, I think data is like paramount, right? So
right.
if you have the knobs and the hooks to actually handle and manage your data with a good quality, I think you have an AI ready model, right? So, and I think the last thing I want to touch upon is I think AI is a co-pilot, right? Again, it's
Mm.
not like a replacement. So I think many people have that impression. Okay, is AI gonna replace a design engineer? Is AI gonna replace an actual product? So I don't think that's, at least for now, that's I don't see that that's happening, right? Because in order to leverage AI, you need a human touch again, right? So the question is
Yeah.
about what are the outputs, what are the limitations that AI might have, right? And exploring those as fast as possible. So I think that those are the key things. I think I would say start small, start fresh, but be smart about it, and then scale yourself up, right? So
Yeah.
it's all
Yeah.
about that.
Just one last point then, because you talked about continuous learning.
Mhm.
I'm going to ask you to be a little bit of a crystal gazer. Well, what do you see as sort of next steps in sort of 3D IC design and AI and the AI tools? I mean, from what you see in research and papers, is there anything interesting
Of course.
that you've come across which our viewers might want to sort of listeners and readers might
Yeah,
want to
I think one
uh,
of the key things that I came upon, and one of the key things that I'm interested and I'm doing research right now, I can share that is, basically how can we extend agentic AI frameworks to actual physical AI? Thermal is kind of producing all of these. How can you have physical AI, create a thermal model, keeping all of these in the fabrication, in the labs, or
mm,
in the
mm,
manufacturing areas, right? How can you help physical AI create like hybrid bonding, right? Or nitro bonding, or especially in CoWoS, or all of the next SOICs that we see from different foundries. How can physical AI, and I think design teams or foundries have been actually wanting to do this from a long time, and I'm pretty sure that many of them have engaged in physical AI as well. But I think that's going to be our next wave, right? Where you have an agentic AI model that you have built using DSE and then LLMs, and then now you're taking it to the next stage where now you have physical AIs, especially in autonomous driving, autonomous cars, automobile, or any other chips. How can you
right.
actually help build it and then scale it up? So I think
Okay.
that that's going to be our next hot topic, is what I see.
Okay. Well, Sudarshan Deo, thanks for joining us on this edition of Silicon Grapevine, brought to you by Siemens Digital Industries Software. And, look forward to engaging with you on future conversations.
Thank you, Nitin. Thank you for having me. It was nice talking to you.